starting Chapter 6, which is called Differential Equations. In Section 6.1, it's called Slope Fields and Euler's Method. But the first thing we're going to do in Section 6.1 is use initial conditions to find particular solutions of differential equations. We're going to do the slope fields later, and maybe not even do Euler's method. So, general and particular solutions. We've talked a little bit about differential equations before. A differential equation is an equation that involves a derivative of y. A function y equals something is called a solution of a differential equation if when you take the derivative of y and you plug it in, then it equals whatever it says on the right side. So for example, differentiation and substitution show that y equals e to the negative 2x is a solution of the differential equation y prime plus 2y equals 0. Let's actually do this. So we need y prime. This is in the form e to the u. U would be the exponent. The derivative of that would be negative 2. The derivative of e to the u is e to the u times du. So y prime is negative 2 e to the negative 2x. Let's substitute that back in here. So negative 2 e to the negative 2x plus 2 times y, and our original y is e to the negative 2x. So you notice if you simplify those two, add them together, you do get 0. So it does work. So e to the negative 2x is called a solution of the differential equation. In fact, every solution of the differential equation would be in the form y equals some number c times e to the negative 2x. Like if we said y equals 3 e to the negative 2x, we're saying that would still be a solution of this differential equation. The derivative of 3 e to the negative 2x would be negative 6 e to the negative 2x. Just using that same work we have up here, we'd have negative 2 e to the negative 2x, then times the 3, this constant here. So then if we plug that in, we'd have negative 6 e to the negative 2x, plugging it into y prime, plus 2 times the original y, which we're saying is this, 3e to the negative 2x. So again, the negative 6 and the positive 6 will add up to 0. So if we plug any number into here, then take the derivative of it and plug it in here, we'll get 0. So this is a general solution of the differential equation that we have above. So do you see the difference between general solutions and particular solutions? This is one particular one, but if we put any number here, that's the general solution. Okay, one thing you're going to have to do in your homework is to verify that things are solutions. So determine whether the function is a solution of the differential equation. So let's take the derivative. We don't need the first derivative, we just need the second, but to get there we've got to take the first derivative. So we have negative sine x. We're going to plug that in here. So we have negative sine x minus the original function, which is sine x. Does that equal 0? No, it does not. So no, sine x is not a solution. How about this one? In this case, u is the exponent, and the derivative of u is negative 1. So the derivative of 4e to the negative x is 4 e to the negative x times the derivative of negative x. So it's negative 4 e to the negative x. Then we need the second derivative, negative 4 times e to the negative x, then times the derivative of the exponent again. So then we get positive 4 e to the negative x. We're going to plug that in. So we have 4 e to the negative x minus y, so minus the original 4 e to the negative x. Does that equal 0? Yes, it does. So 4 e to the negative x is a solution of y double prime minus y equals 0. Here we've got another example. Take the derivative. C is a constant, so it's c times the derivative of e to the x, which is e to the x. The second derivative will be the derivative of this, which will be again c e to the x. So the second derivative minus the original, does that equal 0? Yes, it does. So that's how you verify that a solution is a solution of a differential equation. General and particular solutions. Geometrically, the general solution of a first-order differential equation, first order meaning it has one derivative, like the first derivative in it, represents a whole family of curves. Those are all called the solution curves. So the general solution is like those equations with C in them. There's a whole bunch of C values we could choose, and when you graph them, they create curves. One for each value assigned to the arbitrary constant. So this is our arbitrary constant. So we'd have like 1 over x, 2 over x, 3 over x, any value we could plug in there, and we could have a whole graph full of many curves. So if we verify that y equals c over x is a solution, a general solution of this equation, let's do that. Y equals c times x to the negative 1 is going to be easier to take the derivative of. So the derivative is negative c, because you multiply that out in front, x to the negative 2, subtract 1 from the exponent, which is negative c over x squared. Let's plug that in here. X times y prime plus y, the original y is c over x. Does that really equal 0? Well, this x cancels with one of those, and now we have negative c over x plus positive c over x. So yes, that does work. All right, so we've verified that this is a general solution of this differential equation. Now let's look at the graphs of about 8 different possibilities for c. Here's some. If you put different values for c in here, 1, negative 2. Okay, it's 4 different possibilities, because if you put c as negative 2, you get this part and this part. If you put c equals negative 1, you get this graph with that one. These two go together, and the black ones go together. So there's 4 solution curves, but there's an infinite number of solution curves that we could have. Each solution curve here is a particular solution because it has an actual value for c. And we can get that particular solution by using initial conditions. And we've seen that before with position functions. So that initial condition actually stems from things involving time, where that initial time, or t equals 0. So we've talked about the position functions. Position function's second derivative is the acceleration. So if the acceleration is negative 32 and you integrate that, you'll get negative 32t plus some constant. And we use the first derivative, initial condition, of t equals 0, put 0 in there, and then you get 64, so c must be 64. That's your velocity. That's your initial velocity, is 64. So that's going to go here. And then you integrate that again, so we have negative 32t plus 64 is our velocity. If you integrate that again, you get negative 32t squared over 2 plus 64t plus c. And to get that value, we plug in this initial condition. If t is 0 there and 0 there, this equals 80, so c must be 80. So that's how we get that, because you plug in 80 for c. So we've used initial conditions before. We've got our general solution with the c's in it, and then our particular solution with the actual values in using that initial condition. There's your homework. Page 411, 1 through 51 odd. Please skip numbers 9, 11, and 33.